An important and useful property of electromagnetic waves is that they can be polarized. Now, in previous lectures, we've been drawing our waves like this. If you think about this for a sec like a rope, we can get the wave in the rope to oscillate in the vertical or the horizontal directions. We call this kind of wave linearly polarized or plane polarized, as they are oscillating in a plane. Now just imagine for a moment that we placed a board with a vertical slit in front of both waves. Now the vertical wave would be able to pass through, like this here. However, the horizontal wave would not. Now if we did the same with a horizontal slit, the vertical wave wouldn't pass through, but the horizontal one would. Now, electromagnetic radiation isn't necessarily polarized. It can also be unpolarized, meaning that the source oscillates in many different planes, like this. Whereas plane polarized looks like that. Some sources of unpolarized electromagnetic waves that we see every day come from the light bulbs in the ceiling and also the sun. So, before we get into unpolarized light, let's have a look at plane polarized light to begin with. So we can obtain plane polarized light using a Polaroid sheet. Now, Polaroid materials were invented in around 1929 by Edward Land and are now commonplace in sunglasses, car windows, windows in houses, and a whole lot of other places. A Polaroid sheet is made up of long molecules arranged parallel to each other. It's kind of like our slits from before, but you could think of it as just many of them put together. Now the direction in which the light can pass through the sheet is called the transmission axis. So like here, we have our Polaroid sheet here, which is vertically polarized, meaning that it is a vertical transmission. Any light perpendicular to this transmission axis is absorbed by the sheet, so in this case it would be anything horizontally polarized. We can actually think about this at the atomic level. So the molecules are aligned perpendicular to the transmission axis. Now this seems counterintuitive, but imagine an electromagnetic wave oscillating in the same plane as the long molecules. The electric field can set electrons into motion along the molecules, doing work and therefore transferring energy. Hence, if the electric field is parallel to the long molecules, it gets absorbed. So an electric field perpendicular to the long molecules, on the other hand, does no work on the electrons and thus passes through the material. Okay, let's say we send an electromagnetic wave, this one here, with an electric field strength of E0 at an angle of theta to the vertical. Now we're going to send this electromagnetic wave through our vertical polarized. What I'd like you guys to do now is to use your knowledge of trigonometry and see if you can work out what the equation is for the electric field strength on the other side of this Polaroid.